projects. In this video, we are going to explain about the project entitled as an artificial neural network for short-time air temperature prediction. So before getting into the video, let me give you the brief description about the project. The title refers to a project that uses a computer-based learning model inspired by the human brain to forecast air temperature over a short future period. The artificial neural network analyzes past temperature data and identifies patterns or trends that help it make accurate near-term predictions. This approach is useful because temperature changes can be complex and non-linear, and ANNs are well suited for capturing such relationships to provide reliable short-term weather forecasts. Coming to the abstract states that the project focuses on predicting short-term air temperature, which is important for many real-world applications such as weather forecasting, farming decisions, energy usage planning, and understanding environmental changes. Traditional methods often struggle because weather patterns are complex and do not always follow fixed mathematical rules. To solve this problem, the project uses an artificial neural network, a type of machine learning model that can learn patterns from data on its own. By feeding the ANN with past temperature readings and additional information like humidity, wind speed, and seasonal changes, the model becomes capable of understanding how these factors influence temperature. As a result, the ANN can provide more accurate and reliable short-term temperature predictions. This makes it a powerful and efficient solution for real-time forecasting compared to older, rule-based approaches. Coming to the existing system, in the existing system, air temperature predictions mainly depends on traditional methods like numerical weather prediction models and classical statistical techniques, including linear regressions, arrhythmia, and time series decomposition. These approaches rely heavily on complex mathematical equations and require powerful computing resources to stimulate atmospheric behavior. However, weather conditions are often non-linear and unpredictable, which makes it difficult for these traditional models to accurately capture sudden changes or irregular patterns. They also struggle when the data is incomplete or noisy. Because of these limitations, the accuracy of short-term temperature forecasts can be low, especially when the weather changes quickly. This shows that there is a strong need for smarter and more flexible models that can handle complex climate patterns more effectively. Coming to the proposed system or base paperwork, the proposed system uses a machine learning approach, specifically an artificial neural network, to improve the accuracy of short-term air temperature prediction. Unlike traditional mathematical models, the ANN can automatically learn complex patterns and hidden relationships from historical weather data. This makes it more effective in handling non-linear climate behavior, sudden changes, and irregular patterns. The system can be built using advanced neural network structures such as multi-layer perceptrons or recurrent neural networks, including LSTM models, which are especially good at understanding time-dependent data like temperature sequence. Before training, the input variables such as previous temperature values, humidity, wind speed, and seasonal effects are pre-processed and normalized to ensure high-quality learning. The network architecture is then optimized by selecting the right number of layers, neurons, activation functions, and training parameters. After training with enough meteorological data, the ANN becomes capable of producing high accurate short-term forecast. This approach is more efficient because it reduces the need for heavy mathematical computations and adapt quickly to real-time changes, make it far more flexible and reliable than traditional forecasting methods. Coming to the dataset, we have used the air quality monitoring in European cities dataset. Is a rich and detailed spatio-temporal datasets created to study environmental conditions across various European urban regions. It brings together three major types of information like air quality measurements, meteorological data, and spatial or land use details, making it highly valuable for understanding how pollution behaves over time and across different locations. The data is collected on an hourly basis from 2020 to 2023, allowing researchers to observe short term fluctuations and long term trends. It includes key pollutants such as particulate matter or nitrogen compounds, along with weather related factors like temperature, humidity, and wind, which are known to influence pollution levels. The dataset also contains geographical context represented on a 0.005 degree spatial grid, meaning each data is tied to an exact location, enabling moderately detailed mapping of pollution intensity across city regions. Because it combines time based, weather based, and location based data, the dataset supports advanced analysis such as studying how pollutant variance throughout the day, how meteorological changes impact air quality, and how different land use types such as residential, industrial, or green areas affect pollution distribution. Its structures also make it ideal for training machine learning models, performing environmental forecasting, conducting exposure or high risk assessment, and supporting urban planning decisions. Overall, this data set provides a powerful foundation for deep and meaningful research into air quality dynamics in European cities. Coming to the novelty or extension or enhancement or improvement. As an extension, several advanced techniques were integrated into the system to further enhance prediction, accuracy, model interpretability, and user accessibility. First, standard scaling was applied to the input features used in the LSTM and GRU models to ensure proper normalization, allowing to neural networks to learn more effectively. Through this enhancement, the models achieved strong performance with MSE values of 0.15 and 0.19 for test set 1 and 0.81 and 0.15 for test set 2, showing improved accuracy across various testing scenarios. Next, we also applied explainable AI methods, especially live and sharp, were implemented to analyze and visualize feature importance, helping users understand how each input variable contributes to the final prediction. Finally, a user-friendly interface was created allowing users to input meteorological values and obtain real-time temperature predictions from the trained models. These extensions collectively enhance the system's performance, transparency, and practical usability. Coming to the flow of the work, firstly, we need to import the packages. We import all the required Python libraries such as Pandas, NumPy, Scikit-learn, TensorFlow, Keras, Matplotlib, Lime, and Sharp, and JobNet. These packages provide essential tools for data handling, pre-processing, model building, evaluation, visualization, and explainability. Next, exploring the dataset. In this step, the air quality monitoring in European cities dataset is loaded. Then we have pre-processing the dataset. The dataset is split into three sets on training set and two testing sets to evaluate how model performance under different conditions. The temperature values are normalized with respect to a maximum possible temperature of 50 degrees Celsius, ensuring stable model training. The hover features is scaled to represent to hour of the day properly and help the model learn daily temperature patterns. The time series data is converted into supervised learning format by creating input-output pairs where past values are used to predict the next temperature values. Next, train test structuring. Here, the prepared train and test sets are reshaped and formatted to match the input structure required for various deep learning models like LSTM, GRU, and ANN. This ensures that each model can correctly process sequence of time series data. Next, we have building models with hyperparameters. Multiple predictions models are built to compare the performance. Like base models are linear extrapolate. It predicts the temperature based on the linear trends. Constant extrapolation, LSTM and ANN hybrid, it combines of LSTM layers and dense layers. FF and ANN, feed forward artificial neural network. It is a fully connected neural network. And as an extension, we have done the normalization with standard scalar. Standardizes feature values to improve the training efficiency. And we also use deep learning models like LSTM and GRU. Next, we have model evaluation. Each model is tested on the two test sets using evaluation metrics such as RMSE and MAE. RMSE is known as root mean square error and MAE is known as mean absolute error. These metrics helps measure how accurately the models predict temperature. The model with the lowest error is considered the best performing model. Next, generating comparison graphs. Visual comparison graphs are created for all models showing their performance scores on both test sets. This helps in analyzing which models performance better and how they differ in accuracy. Next, we have save the best model. The best performing model is saved using Joblib, allowing it to be loaded later for real-time predictions without retraining. This is important for deployment in user applications. And next, explainable AI techniques. To understand how each feature contributes to the model prediction, LIME and SHAP are implemented. These explainable AI techniques visualize feature importance, providing transparency, and helping users trust the model output. Coming to the front end, a front end interface is developed using the Flask framework. It includes user registration and login and SQLite database for authentication and storing the information. On the front end, the user enters required meteorological inputs like temperature, humidity, etc. These values serve as a feature for the prediction model. Before prediction, the inputs are pre-processed in the same way as the training data, such as applying scaling or normalization, ensuring the consistency. The previously saved model is loaded into the Flask app so that it can perform real-time predictions. The final predicted temperature is displayed on the front-end interface, providing users with an easy to understand result. The algorithms used in the project are linear extrapolate, constant extrapolation, LSTM ANN, FFANN, LSTM, and GRU. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consist of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project's code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the project execution, firstly, copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The homepage of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Sign Up button. Now, click on Sign Up button so that Logon HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, email ID, mobile number, and a strong password. Then click on Create an Account so that all the given details are stored in signup.db and the login HTML will be opened, where you need to access the application by username and password. Then click on Sign In. The prediction page has been displayed. In this page, we have Home button, Prediction button, Data Analysis button, Notebook button, and Sign Out button. Firstly, we need to click on Prediction button so that the prediction page will be opened, where you need to give the input values of the temperature and predict the output. So these are the three inputs where you need to give the values. First, we need to enter the temperature in 2 hours. Next, we need to enter the temperature in first hour. Then we need to enter the temperature in 0 hour. Now click on predict so that the input values are pre-processed and the output will be displayed as the input data. Your temperature inputs are like first hour, it's 56.79 degrees Celsius, and second hour, it's 23.46 degrees Celsius, and third hour, it's 26.32 degrees Celsius. So that the temperature is predicted as for 1 hour in short-term forecast, for 4 hours, the medium-term forecast, for 12 hours, the extended forecast, for 24 hours, the long-term forecast. Based upon this, we have the visualization of the temperature trend analysis. On the x-axis, we have the hours. On the y-axis, we have the temperature. And the prediction analysis and insights are given as temperature trends and 24-hour forecast. We also have some useful information like understanding your predictions, how to use the predictions, practical applications, and important note. So here we have make a new prediction. When you click on this button, again, you reaches the prediction page where you need to give the input values and predict the output. So next, click on data analysis so that the graphical representation of the projects will be shown here. Firstly, we have test 1 MSE graph. The graph mirrors the same comparison as graph. The graph represents the CE model has the highest MSE by a wide margin, comparing its poor compatibility with the dataset. The LE, LSTM and GRU models have very small MSE values, showing their predictions stay close to the actual targets with minimal errors. The FFANN and LSTM-ANN models perform better than CE, but not as well as the recurrent architectures. This graph reinforces the consistent pattern that recurrent neural networks like LSTM and GRU are best performing models to test one, providing the most reliable and stable predictions. And next we have test one RMSE model graph. The graph illustrates the root mean squared error for the same set of machine learning models on the test 1 dataset. RMSE is the square root of MSE and is expressed in the same unit as the predicted values, making it easier to interrupt. Again, the CE model exhibits a very large RMSE, signaling large deviations between predictions and true outputs. Models such as GRU and LSTM display very low RMSE, reinforcing their ability to generalize well on sequential data. The LSTM ANN and FNN models perform reasonably, but not as well as pure sequence-based models. Similar to the test 2 results, this graph highlights that deep recurrent architectures maintain superior accuracy, while the CE model continues to underperform dramatically. Next, we have test 2 MSE graph. This graph compares the mean squared error of different machine learning models on the test data 2 dataset. MSE measures the average squared difference between predicted and actual values. So, lower MSE means better predictive accuracy. In the chart, the CE model stands out with an extremely high MSE value, indicating very poor performance and large prediction errors. In contrast, models such as LE, LSTM and GRU shows very less MSE scores, suggesting they capture the underlying data patterns much more effectively. The FFANN and LSTM-ANN hybrid models perform moderately, falling between the extreme values of CE and the strong sequence models like GRU and LSTM. Overall, this graph shows that deep learning sequence models outperform classical or engineered approaches on test 2. Next, we have test 2 RMSE by model graph. This bar graph compares the test 2 prediction errors of different ML models. Lower RMSE means better performance. CE has the worst accuracy with a very high error. Models like LE, LSTM ANN and FFANN perform moderately. The best performers are LSTM and especially GRU, which has the lowest RMSE and therefore the most accurate predictions. And next we have explainable SHAP summary plot graph. The SHAP plot shows how three features T0, T2 and T1 influence the model's prediction. Points further from 0 on the x-axis have stronger impact. T0 has the widest spread, meaning it is the most influential feature. The color shows feature values from blue, which means low, to red, which means high. High values of T0 tend to increase predictions, while low value decrease them. T1 and T2 have smaller spreads, meaning they contribute less to the model. Next, click on Sign Out. So finally, in this project, we demonstrate how artificial neural networks can effectively predict short-term air temperature with high accuracy. By training the model on historical weather data, the ANN was able to recognize hidden patterns and forecast temperature, changes that traditional methods might miss. This result highlights the power of machine learning in environmental monitoring and open the door for smarter, data-driven decision-making in areas such as agriculture, energy management, and public safety. As technology continues to advance, ANN-based prediction models will play an increasingly important role in building more resilient and sustainable systems. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.